'cause in the end, for you and me, radioactivity.
Okay, if you can't see my screen share, say something, otherwise I'll just keep going. Okay, so let me put in all the caveats. What I'm going to talk about next are radioprotectors. This is a relatively short section because we don't have that many radioprotectors. There's a lot of work being done on new mitigators right now, but I haven't seen any of them make their way into the boards, so I'm not going to emphasize those. I'm going to emphasize the ones I've seen on the boards. A radioprotector by definition is anything that directly protects. There are some indirect protectors that cause changes in blood flow that seem to make a difference. But the main ones we'll be talking about here are direct radioprotectors. And what, if you remember in the very first section we talked about, was that anything that has a free self-hydral group on it is capable of being a radioprotector because it eats up free radicals. So here's cysteine, cysteamine, both are free radical scavengers because they have this free SH group. So we have this quantity we calculate for radioprotectors, and it's called a dose reduction factor. It is really important to remember this. There is a board's question that says, which of the following compounds has a dose reduction factor? And the answer is the only one that's the radioprotector on the list. So you've got to remember it, and it is the dose of radiation in the presence of the drug compared to the dose of radiation in the absence of the drug to produce lethality. Usually, the functional group that is on radioprotectors is a free SH group. And if you see any chemical with a free SH group, you can guess that it's a radioprotector. Sometimes there's some that have strong basic functions as well, particularly amine or guanidine residues. Here's the kind of concept of the radioprotector. You give radiation, it hits the DNA, it causes a free radical to form. The free radical is eaten up by the thiol, the free thiol group, the SH group that is present, and makes the DNA miss this free radical. This is in contrast to something we'll talk about much later here called radiosensitization, where we get the fixation of the free radical damage, and that leads to more killing of cells. Obviously, we want radioprotection to occur in normal tissues, and we want radiosensitization to occur in the cancer. And it comes back to the same thing I told you back in the first lecture that was going to be important. I said to you, we're going to talk about this direct versus indirect action. The free radical scavengers are going to work on indirect action. Here's the radiation hitting the water molecule, giving rise to the hydroxyl radical. This is eaten up with the self-hydral group, which converts this, two self-hydral groups will convert this back to peroxide eventually to water and prevent this from taking place. So maximally scavenging free radicals should cause a dose reduction factor that's very close to the OER. But one thing that should be said, and this is somewhat controversial and nobody quite understands it, some radioprotectors do work with high LET radiations. They shouldn't, but they do. And in particular, their data say that they do work with neutrons. So that's it's a minor way in which they work. It's not the major way in which they work, but there probably is another mechanism by which these radioprotectors are functioning within cells. Okay, here is beta-mercaptoethylamine. This is a compound that was first found. Free self-hydral groups on it have dose reduction factors of 1.6 and 2.1, and they were among the first radioprotectors that were used. They then kept working on developing new ones. Here's one called Cystophos. It's got a self-hydral group here, and this was carried by the Russian army in their field packs. The most important radioprotector you need to know for your boards is this compound right here called amifostine. It is used in clinical radiotherapy and is also used by the astronauts when they go on lunar missions. It's got a dose reduction factor of only 1.8 at 7 days, but at 2.7 up to 30 days. So you're going to say, I don't remember anybody talking about amifostine used clinically. And I will tell you, it is not commonly used. The main examples I saw for it to be used were like in salivary glands, where they would give amifostine to protect salivary glands during head and neck irradiations. I'll tell you, we'll look at some of the clinical data on it. It's not used as much as it could be, but it is also used by the astronauts when they're going up into space as one of the few things that can reduce their radiation toxicity, and that is, and they do carry amifostine with them. Both the moon and the Mars mission will probably also carry it. Okay, so here's what you need to know, handy dandy facts about amifostine. It got its name back here, WR2721, and it's called WR because it was developed at Walter Reed Hospital. So anything with a WR in front of it was Walter Reed. WR2721 was the patient they gave, the drug that they gave to patients. It's actually a prodrug, and in the body it becomes WR1065. So if you were to add one of these to culture, you would add WR1065 to cells in culture. WR2721 is metabolized to the body to its active ingredient. So the prodrug goes to the liver, is modified by alkaline phosphatase, which takes off the phosphate group, converts the inactive prodrug into the active drug. So this is the inactive drug, this is the active drug. So this is the prodrug versus the drug. There is more transport of the drug to normal tissues than to the tumor, so therefore it gets a higher accumulation in normal tissues. We'll look at those data in a moment. We usually give the drug minutes before radiation exposure to decrease normal tissue toxicity. It gives good protection for the hematopoietic system, the gut lining, and the salivary glands. It gives pretty much no protection for the CNS, so therefore it's not going to be useful for the CNS. It doesn't cross the blood-brain barrier. It's hydrophilic in nature, and this is probably the reason why we find a better uptake in normal tissues than in cancer, although I suspect there's something more than that to this difference. The dose-limiting toxicity is hypotension. Please remember that that's a board's question. It's also called ethiol, and it is one of the few FDA-approved drugs for use as a radioprotector. Here are the data. This is a rat given amifostine, looking at what gets where the amifostine goes. It goes poorly to the tumor. It takes 90 minutes before it's going to the tumor. It goes to the rest of the tissues pretty well. So therefore it's going to give, during these early times, it's going to give better protection of normal tissue than it will for the tumor. This animal was given radioactive amifostine, and every place you see black is where it accumulated amifostine. Bone marrow, kidney, lungs, but tumor is white, brain is white. Doesn't cross the blood-brain barrier, doesn't cut into the tumor very well, so therefore it's not going to protect those tissues very well. Here's the kind of data you get with it. Log rank fraction against dose, no drug, amifostine. You can see this is a significant dose reduction factor there. And here are the protective levels that one finds for these different organ systems. Pretty good protection of the salivary gland, which is why they use it often. Not protective of brain or spinal cord, so it's not going to work in the CNS. Now, there's a history of it's being used in the clinic. It was first used actually in China. They gave 100 patients radiotherapy. They're hoping to look for protection against damage to the skin, mucous membranes, bladder, pelvic structures, and a whole bunch of other stuff. The problem was the Chinese physicians did not believe that the radioprotector was going to work effectively on they expected it to protect the tumor too. So unfortunately what they did is they gave an increase in radiation dose. This gave increased normal tissue damage. So it was a very poor study. It didn't work very well. There are also some data that suggests that it protects against chemotherapeutic drugs because that work by a similar mechanism of DNA damage. Here are some animal data looking at control and amifostine, and they looked with for mucositis that was developing in these animals, and of course they're showing that amifostine does give a bit of a protection here in these animal systems, and that's the amifostine story. Let's move on to a second set of radioprotectors that have not made their way into use clinically all that much, but there was a board's question on it 3 years ago. Okay, so MnSOD, manganese superoxide dismutase. Superoxide dismutase is a natural free radical scavenger that's found in the body. It is normal. It's found in our genomes. There are two other superoxide dismutases, SOD1, which is copper zinc SOD, SOD3, which is extracellular SOD, and SOD2 actually, which is MnSOD. It's been tried in gene therapy to protect from late effects quite successfully. There's now a drug that mimics MnSOD. It's a porphyrin derivative. It's got this huge name here. And it behaves as an antioxidant. Here's the thing that's weird, is we don't have any evidence that protection of mitochondria should make a difference, and yet SOD2 accumulates in mitochondria, prevents the generation of reactive oxygen species there, and gives few toxic products. So how it exactly works as a radioprotectant, not really clear. It has not found its way into heavy use in the clinic, despite efforts. There are other nutrients that have been proposed, and nutritional elements that have been proposed as radioprotectors, vitamins, things, a lot of these that contain sulfhydryl groups, thiols, curcumin, and many of these have been shown, garlic extracts, many of them have been shown to have some slight effects, but most of them are not at the level of what we see with amifostine. I love this report out of Japan where they looked for beer as a radioprotectant, and of course it was quite successful. I wondered whether this was funded by one of the beer factories in Sapporo, but they claim it wasn't, so I find that interesting. There's one other agent that has been used as a radioprotectant. It works in an indirect way. It was actually first studied by Bill Small, who's currently at Loyola. He did this work when he was at Northwestern. And what they argued was that the drug pentoxifylline was being used clinically to improve circulation. So if you improve circulation, could you somehow prevent late tissue toxicities, especially those that are responsible for fibrosis? This made sense. They tried it. They had some good success with it. And in fact, what pentoxifylline seemed to do is to interfere with the cytokine cascade. There was a question about what its mechanism is on the boards. It inhibits TNF alpha and other cytokines involved in the development of fibrosis. Is it used clinically that much? I would argue not that much. It had a lot of hope, but most of these have fallen by the wayside and have not led to successful use. So here's our candidate here that is the best candidate we've got right now, amifostine. It is the thiol compound. It is the free radical scavenger. It's got WR2721 as its name. It's also got WR1065 as the active metabolite. We will learn about these other radiation response modifiers that are radiosensitizers or work in hypoxic conditions later in this course, but the focus here is right now on the radioprotectants, and amifostine is one. Now, I mentioned already when we talked about terrorism, the decorporation agents, you should know that DTPA is a decorporation agent. It can take cesium or plutonium even out of the body. There's another dye called Prussian blue, which does something very, very similar. And that potassium iodide is a blocking agent that can be administered to people and can quite successfully block iodine uptake into the thyroid. I will mention that there are several other new agents that are being pursued by the National Institutes of Allergy and Infectious Diseases. We collaborate with somebody who's working on a drug called HOPO, which is also a decorporation agent. I think we'll be seeing more stuff coming forth in the following years, but I don't see them as being on board's questions, and that's why I'm not going to emphasize them here. So summary is amifostine is the most important radioprotector used clinically today. The dose reduction factors are often used to determine how effective a radioprotector can be, and new radioprotectors exploiting superoxide dismutase and other pathways are being explored, but we really aren't there with any of those yet. And that's topic 9. I think we have 15 minutes left, but I have to do another lecture at 11 to a group of undergraduate students. So I'm going to end this with this lecture, and tell you the truth, it wouldn't be a good thing to start topic 10. I'd just get into it and then we'd be gone. Topic 10, the next topic we'll talk about next week is going to be radiation carcinogenesis and how the Japanese atomic bomb survivor data and other data led it into our understanding of how radiation causes cancer.
Radioactivity is in